Hello friends, welcome to engineering tutorial. So in the previous video we discussed about the output response of a first order system to unit step input. So in this video we are going to analyze and study the output response of a first order system to unit impulse input. Okay, so previously we did it for the unit step input. Here we'll study it for unit impulse input. Okay, so this is again a standard representation of a first order system, and we have again a unity feedback, negative feedback system, and the closed loop transfer function Cs by Rs. I'll write it down directly, which is 1 by S T tau plus 1. Okay, or we can write it as 1 by tau by S plus 1 by tau. Okay, both ways of representing the closed loop transfer function. Now I've already explained the design of a first order system in the unit step video, so you please check out that video first so that you understand these things in a better way. Now this is the S domain representation of the output and the input, the ratio of Laplace transform of output and input. Now again here we are analyzing the output response for unit impulse input. So I have already discussed about the various types of inputs that are used to test control systems. So the unit impulse input, it exists only at t equals to 0. Okay, delta t equals to 1. This is the unit impulse input, and another important characteristic is that the Laplace transform of the unit impulse input is equal to 1. Okay, these are the important things that we should remember. Okay, so here CS, we have to study the behavior of CS. So if we have to study the behavior of CS, we have to take this Rs here. Now again, important thing to remember is that RT is equal to unit impulse input. So Laplace transform of RT, that is Rs, is equal to 1. Here I just told you this is the important property. So it means simply this side would get multiplied by 1. Okay, so CS CS is equal to 1 by tau by S plus 1 by tau into Rs, which is equal to 1 because Laplace transform of unit impulse input is equal to 1. So we'll write here 1. Now this is the representation of the output response for a first order system to unit impulse input. This is the S domain representation, but we need the time domain representation. So what we'll do, we'll take the Laplace inverse of the S domain representation. Okay, so here some concepts related to Laplace transform will come into play. So a basic formula related to Laplace transform, it says that Laplace transform of e to the power minus at, okay, Laplace transform of e to the power minus at exponential signal with a being any constant value. It is 1 by s plus a. Okay, this is the Laplace transform of the exponential sigma. Okay, so if we substitute a with 1 by tau, okay, just try to correlate these two. Replace a with 1 by tau. So Laplace inverse of 1 by s plus a will be then equal to e to the power minus at. So here the Laplace inverse of 1 by 2 by s plus 1 by tau, okay, 1 by tau by s plus 1 by tau, it will be e to the power 1 by tau e to the power minus t by tau. Okay, so it will be 1 by tau e to the power minus t by tau. 1 by tau is a constant, it will be kept aside, and Laplace inverse of s plus 1 by tau, as per this formula, according to this formula, it will be e to the power minus t by tau. A is 1 by tau. Okay, so the Laplace inverse of this, Laplace inverse of 1 by tau by s plus 1 by tau is equal to 1 by tau. It will come out as it is a constant. Laplace inverse of 1 by s plus 1 by tau, so it will be 1 by tau e to the power minus t by tau. Okay, this is equal to Ct, which is the time domain representation of a first order system to unit impulse input. Okay, this is the time domain representation, and this is the S domain representation. Okay, so this is the time domain representation. So we just determined the time domain response of a first order system to unit impulse input. So if we study this output response, we will find that it closely resembles discharging equation. Okay, discharging equation in RL and RC circuits in transient analysis. Okay, the discharging of inductor current and the capacitor voltage. So what will be the shape of this waveform? So at t equals to 0, okay, at t equals to 0 and at t equals to phi, we will try to plot these points. So at t equals to 0, it will be 1 by tau e to the power minus 0 by tau, which is equal to 1 by tau. Okay, and at t equals to infinity, means steady state or steady state, it will be C infinity 1 by tau to e to the power minus infinity by tau, which is simply 1 by tau into 1 by infinity, which is equal to 0, as 1 by infinity is 0. So at t equals to infinity, the value is 0, the output value is 0, and at t equals to 0, and means at start it is 1 by 2. So it has a maximum value at t equals to 0 and 0 minimum value, which is 0 at the steady state. So it is a standard discharging equation. So its shape, the waveform shape will be like this. Okay, this is Ct, this is t. At t equals to 0 it was 1 by tau, and at t equals to infinity means steady state, it had a value 0. So we will simply join these points. Okay, so this is the waveform, the shape for a first order output of a first order system to unit impulse input. Okay, so we have covered two portions related to first order system, the time response analysis for unit step input and unit impulse input. So remaining one is the unit ramp input. So we'll discuss it in another video. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to electrical, electronics, instrumentation and communication engineering. Have a great day. Thank you very much.